Today's lecture is about convergence of Fourier series. So we already discussed how to calculate the coefficient of the Fourier coefficient of a function, of an L2 function, and we calculated the Fourier series of 3 different functions. And there was a question that does this infinite sum make sense? Does it converge? And if it converges, does it converge to my own function? And we saw examples that at some point it converges to my own function and some other point it does not. But I mean, let's see graphically at least what's going on. So let's start with our function. So we defined f of x to be, for x between minus pi and pi, I defined it to be the function x. And then I obtained the Fourier series of x, let's call this big f of x, to be equal to summation, summation from n equal 1, I will put big N here, of minus 2 into minus 1 power n over n times sine nx. Okay, and let's see what's going on. So let's say n, I want to move n from 1 to 50 or 200, okay, with a step of 1. So for n equal 1, I get the function, replace big N equal 1, you get the function minus 2 times minus 1 power 1. So this is 2 sine x, okay? And then this is the blue curve, you get the function 2 sine 2x. It seems to be a bit far from my function. So let's see if I increase my n a little bit. So this is for n equal 3. You see how the Fourier comes. So the n equals 3 means I'm adding for n equal 1 plus n equal 2 plus n equal 3, this partial sum. And then the function seems to get, so look only now at minus pi and pi. Don't worry about things that are outside minus pi pi. But it seems that my function is like oscillating near the red graph, and the red graph is my original function of x equal x. Let's go to n equal 10, and you can see the convergence. And then here, your function is getting closer and closer, and you can notice that your Fourier series is converging to your function when x is between minus pi and pi, strictly between minus pi and pi. You can see now this is like n equal 54, okay? You can see now you cannot even differentiate the blue and the red thing. But what's going on outside minus pi and pi, what's going on, we know that the Fourier series is a 2 pi periodic function. So outside minus pi and pi, it should converge to something like the 2 pi extension of f. So let's just stop this for a while. Let's hide the Fourier series and let's draw the 2 pi extension. So this is g of x equal fx plus 2 pi. And let's draw also h of x, which is equal f of x minus 2 pi, by switching my function, by making my function 2 pi and 2 pi period. So you can see, okay, now let's activate my Fourier. You can see now also that my Fourier series really converge to the 2 pi periodic extension of my function, except where? What's going on? Where do I have trouble? I have trouble at the discontinuity point. You can see here to the left at minus pi, my function is, I guess, pi, and to the right of minus pi, my function is minus pi. So the Fourier series somehow takes the value 0. You can see it takes the average of pi and minus pi. You can see this closer and closer, like the line is like somehow converging to something vertical. And you can see the convergence. So I'm converging to my function, to my like 2 pi periodic extension of my function, except at this continuity point where it seems that my function is taking the average of the two values pi and minus pi. Why pi minus pi? Because f of minus pi, if I'm going to the right, from the right, it's a function f of x, which is equal to minus pi. But if I go from the left, which is a 2 pi periodic, which is just a function of g of x, then my function is equal to pi. Something else I want you to notice, that it converges well at continuity point, but near this continuity point there's something going on. You can see that there's a peak here. You can see the peak near the discontinuity point. It doesn't go down directly to my point of convergence, but it makes like a jump here. And this jump you can prove, well, it's an exercise in your homework. It's 9% of the jump, which means your function jump from pi to minus pi, which is a 2 pi jump, yes? Then your Fourier, the magnitude of this peak here is 9%, is about 9% of your jump. And this is called Gibbs phenomena. Okay, it's a physical phenomena. It's unavoidable if your signal has this continuity point, and it's kind of make a noise. I mean, in the signal, but you cannot. Let's say it's unavoidable if your signal is discontinuous. Okay, so to summarize from this graph that I have, it seems that my Fourier series is converging to the 2 pi periodic extension to my function, except at discontinuity point. Discontinuity point not of my function, of my 2 pi periodic of my function, of the whole extension, where at discontinuity point it seems to converge to the average value. One more thing is that the convergence looks nice at continuity point, but it looks bad at discontinuity point because of this Gibbs phenomena, where I have a jump and then I go to my discontinuity point. And you can see that the magnitude of jump, although I take more and more value, doesn't seem to change much. Okay, so this is for my first example. Let's see my second example, where I had, okay, let's hide G and H and my Fourier series. My second example was f of x equal absolute value of x. Okay, and in this case, my the 2 pi periodic, this is how I make it 2 pi periodic extension. And now let's see the Fourier series. This function, the 2 pi periodic extension of my function f, seems to be continuous everywhere. Well, it's not differentiable here because I have a corner from the left and a corner from the right. But let's see if this is a problem. And we obtained that the Fourier series, if you can look at the last week note, is pi over 2 minus 4 over pi cosine. Okay, so I have to erase this. Cosine 2n plus 1 x over 2n plus 1 squared. Okay, and this is my Fourier, and this is for n equal to 1. Okay, seems far from my function, but let's see what's happening when, and this is not good. So it's pi over 2. Okay, something is wrong here. Sorry, so it's pi over 2. Yes, the summation from n equals 0 to infinity. Good. Okay. See, it's already very close. I mean, starting with n equal 1, your function, your Fourier is in blue. Okay. And the other thing is your function. It start by being closed, and you can see that for n equal even 6, after 6 term, you cannot even differentiate your function from the Fourier series, and now like they somehow coincide. Okay, and you see you have convergence at every point, even at point of non-differentiability. So the continuity here is that the continuity in the previous section, in the previous example, was a breaking point, but here, as long as I have differentiability of my function from the left and from the right, I'll tell you what I mean. So you have differentiability here from the right, and you have differentiability from the left, and this is what makes it a corner. So you have no trouble, but you have continuity at every point. I mean, you can extend your function even more. So this m of x equal f of x plus 4 pi, and like n of x equal f of x minus 4 pi If you want to continue all your extension, and you can see once I can see. Okay, it didn't like it because it's n. You can see that starting n equal 1, your Fourier series look to be very close to your function, and as n is larger and larger, you cannot even see your function anymore. Okay. Now let's do the last example where I had discontinuity point. So I had f of x equal, okay, let's hide these. So f of x is equal to 0 when x is between 0 and pi, and it's equal for x for 0 smaller than x smaller than pi, my function is equal to 1. Okay, so this is the step function. And now, okay, my Fourier series in this case, if you go back to your example, it's equal to 1/2 plus 2 over pi of sine to n plus 1 in summation to us from 0 and over 2n plus 1. Okay, and it's complaining for some reason. Let's see. Okay, no, it's not. And now you can see that for n equal 1, my function, how my function looks like. And let's make it maybe a little bit clearer. Okay, this is better. Oh, by the way, okay, before that, this was my function. Okay, it's the red thing, and then I extended it by making 2 pi periodic. You can see the 2 pi periodic extension of my function. And now in the Fourier series, now the Fourier series is, I mean, you see at this continuity point, it's between 0 and 1, and it's already very close to 1/2. Okay, and at continuity point, it's converging fast. But look, before the jump, I have this peak that we said is Gibbs phenomena. Okay, and you can see now more and more you have a convergence, and the peak really does not change its amplitude. It should be 9% of the amplitude of my jump, so it will be 9% of 1, and which is 0.09. Yes. Okay, and you can see the convergence of my signal of my Fourier series to my original function. Okay, so that's what I want to show you, because in the next part of this video I'm going to go over the theorem, and I need to do some technical definition. You need somehow your function to be a piecewise differentiable function, and I'm going to talk what piecewise differentiable function is, and then I'm going to state the theorem, which you can see that at continuity point I have that my Fourier series, which means this sum from 0 to n, as n goes to infinity, if x is a continuity point of my function, then the Fourier series will converge to my function. And if x is a discontinuity point of my function, the Fourier series will not converge to my function because I have a jump discontinuity. Okay, you see I have a jump discontinuity. It will converge somehow to the midpoint of the value from the left and the value from the right. Because as I told you, the Fourier series is a coefficient of the Fourier series, which has a0, an, are defined by an integral. So it doesn't matter how you define your function at a discontinuity point, whether you define your function to be 0 at x equals 0 or to be 1 at x equals 0, it won't matter. Or to be half at x equals 0 or to be 5 at x equals 0, it won't matter. But what does the Fourier series does? It does even better than your function. It takes the average. It takes the midpoint of the value from the left and the value from the right. Okay, I'm gonna save this precisely in your next lecture, in the next part of the lecture, and we're gonna state the convergence here. Thank you.